Yeah, thank you very much. I'm gonna still talk about some unusual deposits in Carajás. In part, something that Victor has already added to you, but we are going to investigate two more deposits, the Jaguar and the Castanha, okay, and discuss the origin, if it's magmatic or hydrothermal, okay. So, not moving? Yeah, go. So in the last few weeks, we have seen several talks here in the Nickel Symposium about magmatic deposits, nickel deposits. So they are traditionally linked to mafic intrusions formed due to the crystallization of immiscible metal-rich sulfide liquids, and it's associated with high temperature mineralogy with pyrrhotite, pentlandite, chalcopyrite, and pyrite, less common. But we do have another kind of nickel deposit, which of less importance in terms of economic values, which are the hydrothermal deposits. They are really scarce. The deposits are small, and they are typically composed of lower temperature minerals such as millerite and gersulfite, bravoite, haslevite, etc. And in these deposits, we have more like polymetallic mineralizations. Other metals are associated with nickel. And also they form from the literature as small scale remobilization from nearby mafic intrusions. So interpreted like more like proximal deposits. And bearing this in mind, we're going to investigate textural, a few chemical data, and sulfur isotopic data as well from these three unusual nickel deposits in the Carajás mineral province, to discuss if they represent the orthomagmatic or hydrothermal nickel mineralizations. So a little bit of the Carajás mineral province, just a little bit because it's too complex. And we are located in the northern part of Brazil. So we are in the Amazon craton in the southeastern part, in the border. And Carajás is most well known in the world because of the giant iron deposits hosted by Benedire formations, as well as for the several IOCG deposits that we have in the province. So the IOCG deposits, they distributed along two main sections, or two main belts, as it is called, the Southern Copper Belt and the Northern Copper Belt, okay? And there are a few points that I have to talk about, even though Victor has already introduced the complex geology. So we have to discuss that. Okay, we have magmatism, three main episodes of magmatism. First one between 2.76 and 2.74 billion years. It's associated with both volcanics and intrusive rocks of mafic to felsic compositions. And these rocks are associated with the sedimentary sequence, both the Rio Novo group and the Itacaiuna supergroup, okay? And linked with these volcanic rocks, we have the Serra Leste Suite. I'm gonna talk a little bit more in the next slide. And also the Cateté Suite located in the southern part. Geographically associated with this major shear zone, which we call Canaã shear zone here. And you can see that we have the three deposits located in the map. The GT34 near to the Sossego mine, it's a major copper gold mine in the area. The Castanha also represents a subsided body of the Sossego mine. And we have the Jaguar located here near the Serra Arqueada, and it's a Benedire formation, and two mafic intrusions, the Onça and the Puma complex, okay? One important thing, we have the Rio Maria domain here, with granite, typical TTG greenstone belt to the south. And to the north, we have the Bagajá domain, to which we have a second phase of magmatism related to this. It's syntectonic granites at 2.55. And lastly, this red granites you see spread all over the Carajás domain, but also all over the Amazon craton. They represent A-type mineralizations, granites and associated mineralizations formed at 1.88 billion years. So just to make sure that we have this range here in mind. And since we are envisioning that maybe our deposits are hydrothermal, we have to try to discuss potential nickel source. Okay, so as I told you, in the Rio Maria domain, we have greenstone belts. The Selva and Seringa greenstone belts are formed at 3 to 2.9 billion years. They host comatites with spinifex textured rocks, and however mineral deposits or nickel sulfide deposits have not been described so far associated with these rocks. And then we move to the Serra Leste Suet, 2.76 billion years. The Serra Leste Suet has been investigated for its chromium and PGA rich tenors. And we have the Luanga, Lago Grande, and Formiga intrusions, the main intrusions in the area. And as you can see, with mineralizations, some resource here, you can find more details in the works of Mansur and Ferreira Filho, which are cited here. And I've mentioned too that we have the Cateté Suet 2.74 to 2.73, a little bit younger than the Serra Leste Suet, and also different metallogenetic affiliation. So we have intrusions, the Vermelho, Onça, and Puma, and others. And however, they develop a very deep weathering profile and form lateritic nickel deposits such as the Vermelho and Onça Puma that I'm showing you here. For the resource, the Vermelho is a world-class deposit. And lastly, but not least, we do find nickel in IOCG deposits in Carajás. Is quite common. The IOCG has been dated around 2.74 to 2.73. They are coeval to the Cateté Suet, which is a little bit younger. And we do have nickel and PGE as occurring as accessory phases in these deposits, such as nickel pyrrhotite, cobalt pentlandite, sigenite, nickeline, palladium melonite, among others. Okay, so this is our scenario for nickel. And more recently, these three deposits have been described in the literature. We're talking about steeply dippling ore bodies. They are lens-shaped and they occur along or near the regional scale shear zones, such as the Canaan, as I showed you. And in all these cases, you can see this vertical structure in the cross sections, and they are hosted by either granitic, intrusive, or subvolcanic felsic rocks, and dated at around 2.74 to 2.82 at the GT34, a little bit older, and especially associated with the IOCG deposits in the Southern Copper Belt. Okay, this geometry, this lens-shaped vertical geometry, hosts mineralogy mainly dominated by pentlandite as the nickel ore, and variable proportions of pyrrhotite as well. And magnetite can be found in some deposits, and some of them, especially in the JAGUAR deposit. And in all of them, we have polymitic matrix dominant breccias, as well as veins, and maybe some replacement type deposits can form as well. And the textures that we observe in both the gangue and the ore suggest the same cinematic mineralizations. It's interesting to say also that the nickel ore is preceded by, in all these deposits, by calcite ion hydrothermal alteration. And so the main minerals in the breccias, the main fragments within the sulfides are hornblende, apatite, chloroapatite, allanite, and sometimes magnetite is associated as well. Okay, so the GT34, just briefly, Victor has already discussed it with you, but I have a few highlights here. We have hydrothermal orthopyroxene, which with the scapolite sets up the temperature to up to 700 degrees to these rocks, to these hydrothermal rocks. We're talking about hydrothermal orthopyroxene. And in these breccias, apatite is a very common mineral, and its chloroapatite is really light hair rich, so we form monazite in the contact between the sulfide and apatite. And pentlandite, it's more like the same in terms of composition with pyrrhotite, and pentlandite can form either blocky minerals or occur as flame-max solutions in pentlandite. We do have some chalcopyrite, but it's really restricted, and pyrite and malachite can form as an alteration of pentlandite. So, so this is for the GT34. I'm going to show you in a minute the chemistry and the sulfur isotopes. I'm going to just start with the rocks. So the Castanha deposit here, it's a bit different, and it's more like a replacement type deposit. As you can see, this is a subvolcanic rock, a subvolcanic felsic rock with the quartz phenocryst preserved, but the matrix is completely transformed and altered to form the sulfides. And in these rocks, we do have chlorine apatite, but allanite is also abundant. And some data from Pestillo, 2020. It's a very recent paper. He investigated the oxygen isotope signature of several minerals in the mineralization, and a fluid inclusion study as well, and defined that these rocks, these mineralizations formed from hypersaline brines with temperatures of 500 to 350 degrees Celsius. And as you can see in this picture, we do have calcite associated with the sulfides, and in calcites we have several mineral inclusions, sulfide mineral inclusions. They're pyrrhotite and pentlandite and chalcopyrite as well. And carbon isotopes indicates that these carbonates are of magmatic origin. In the Castanha, conversely, when compared to the GT34, we have much more pyrrhotite, and then chalcopyrite and pentlandite. It's more like a restricted phase, occurring especially as flames, sometimes, as we see here, as blocky minerals. Again, pyrite and malachite form a secondary alteration mineralogy from the alteration of pentlandite and nickel pyrrhotite. And the JAGUAR deposit, particularly, is the only one that is located near traumatic rocks, which is the Puma Onça complex, which could be potential source for nickel. However, in the JAGUAR, we have a little bit a distinct mineralogy. It's a really magnetite-rich deposit. It's the only one that we have resources available for publication here. You can see in the bottom part. Yes, Marco. And pyrrhotite, also the same mineralogy, the alteration mineralogy, pyrite and malachite. And some data, highly variable nickel-copper ratios, and nickel correlates with...
Couple of minutes, yeah.
Okay.
Yeah.
Nickel, just a second. Nickel cobalt correlates well, and low tabs, except for tellurium, low PG contents. We don't just have data for the GT34, and we do have high earth elements contents in these rocks, okay? For the sulfur isotopes, they do show magmatic signatures, a little bit of spread here with a little some more positive values, but they they're representative of the mineralogy that we have, with most negative values in more pyrrhotite-rich deposits, whereas positive values are associated with the JAGUAR, which holds a lot of magnetite. So the Delta 34 deposits points toward mantle-like signatures, and it's correlates with the oxidation state of each deposit here. So magmatic hydrothermal, we don't know. So we have some controversies in these deposits because textures, copper and sulfur signatures favors this magmatic origin, okay? But on the other side, we have hydrothermal alteration, alkalic iron alteration, similar to the IOCG deposits in Carajás, and the fluid inclusion and oxygen isotopic data points toward a hydrothermal model. So we do know that nickel mobility under hydrothermal conditions are quite low. These are some, here you can see some experimental data from Liu, which shows that it's a little bit enhanced when we transform millerite, but really low when talking about pentlandite. So how can we get this sulfur and nickel? Could it come from immiscible liquid from neighbor mafic ultramafic intrusions? But then we have another problem, because this sulfur melts, their high density, low viscosity, so moving it upwards is a problem. And the IOCG nickel that we're calling like that are coeval with the KTT suite, no sulfur saturation at all. So we use the proposed bubbles from James Mungo. Yes. Yeah. Yeah. Okay. So just moving to the conclusions, just to make sure it's over. So GT34 and the Castanha deposits represent a new part of the IOCG. We're interpreting it maybe a new end member. The nickel sulfide crystallization occurring under high temperatures, and we have magmatic source. We could have just a single magmatic source with no external sulfur required, and this hybrid magmatic immiscible melt plus hydrothermal IOCG model could fit into our interpretations. And so these deposits could represent a link between the orthomagmatic and magmatic hydrothermal deposits. So it's a big debate, and we have to keep studying them. So sorry, I have to finish right now. Thanks very much.